Time for 3.3, Cramer's rule, volume, and linear transformations. And I'm going to tell you right now, we're going to skip one of these. We're going to skip Cramer's rule. Cramer's rule is interesting. Don't feel like you're being cheated. I skip this most semesters. I like the idea of Cramer's rule, but it's a cuttable thing from the semester. What it is it's a method of using linear algebra to solve an equation, kind of like the equations we've done earlier, except you can write down the solutions in terms of determinants instead of writing them down by row reducing. It's not as efficient, but it has some really nice theoretical uses, particularly when you start getting into situations where you have complex numbers involved, and it has a real connection with things like Laplace transforms that show up in differential equations. But it's not necessary that you understand how and why this works. So we're going to skip Cramer's rule, and we're going to start with volume and area. So what I want to do is I want to give you a geometry problem to start with. I wrote that problem 3.9, but I changed it. So sorry about that. Make some changes to 3.9 on your own. And these are going to be the changes. Instead of using the points there, I thought these points would be more interesting. So use the point 0, 0, the point 1, negative 2, the point 3, positive 1, and then the point 4, negative 1. And this makes a parallelogram. And see if you can find the area of this parallelogram. I know you don't have to pause it, but this is actually a really interesting geometry problem. So take this, pause your device, just do some geometry, see if you can piece out how to do this geometry-wise. Okay. All right, hopefully you took the time to actually try it and got an answer. There are lots of ways you could do this in geometry class. One way that I like is you draw a big square around it. I don't know if you'll like this or not. One way that I like is you have a big square around it, and then we notice we could take the area of the big square and then subtract off the areas of all these triangles. And so you'll notice our big square has an area, it looks like 1, 2, 3. So it looks like big square is 3 times 1, 2, 3, 4. 3 times 4. So it has an area of 12, and then we'll subtract off the areas of each of these triangles. So this triangle right here, it looks like it has an area of 2 times 1 times 1/2. 1/2 times 2 times 1. And then this one looks like we have an area of 1, 2, 3 times 1. So 1/2 times 3 times 1 plus, and then those two are the same triangles in other versions. So 1/2 times 2 times 1, 1/2 times 3 times 1. And what does this come out to be? This ends up 12 minus, let's put all these, 12 minus 1, plus, that's 1.5, plus 1, plus 1.5. So 12 minus 1, 2, 3, 4, 5, 12 minus 5, and it looks like we get 7. Oh, sorry, I ran out. I was doing that off the screen. So it looks like we get 7 for our answer. Okay, so that's fine. You might guess that because this is a linear algebra class, there's a linear algebra way to solve this problem. And there is. So let me show you the nice linear algebra way to solve the problem. And the way to do it in linear algebra is we can think of this as a vector, and we can think of this as a vector. And if I write those two vectors, my first vector, I'll tell you what, let's make this one my, well, it doesn't matter. My first vector is the vector 3, 1. And my second vector is the vector 1, negative 2. Now the linear algebra way, and what's interesting is not necessarily that is what the solution, but that it works at all. So the linear algebra way is, let's make this a matrix. And then I told you long ago that we should think of determinants as being connected to areas. So let's find the determinant of this thing. And if we find the determinant of this, you'll notice that we have a negative 6 here and a 1 here, and so we get negative 7. And okay, well, areas can't be negative, so that means our area is positive 7. That looks like an area. Okay, negative 7, and so our area is positive 7. So all we need to do is think of the two edges of that rectangle as a, think of the two edges of that rectangle as vectors, and then find the determinant of those. Why do we end up with negative instead of positive? Well, in some ways it's because we went from this vector to this vector, and notice that kind of goes opposite the way the right-hand rule usually goes. And so we ended up in a negative area for our vector. But okay, let's talk about why this works. So why this works is kind of an interesting result. So let me erase this real quick, and I'm going to illustrate this with some popsicle sticks. So, or not some. These aren't popsicle sticks. These are straws. So I'm going to illustrate these with some straws. So I have myself a parallelogram created out of these straws, and I have it from the origin. If it was somewhere else, you just shift it to the origin and make your origin at that spot. So what would be the area of this shape? Well, the area of the shape, what we're going to do is we're going to do some transformations to turn this shape into a rectangle. And so the first transformation that we're going to do is we're going to rotate it until that section is right there on the x-axis. So the first thing we're going to do is we're going to take our original shape and we're going to rotate it. And then once we rotate it, well, you'll notice this looks like a shear transformation. So what we're going to do is we're going to unshear the transformation to make it a rectangle. So we're going to rotate and then unshear, which is actually shearing it, but shearing it in the opposite direction. I wasn't able to quite do this right. If it was correct, it would be that length, but these popsicle sticks, I can't change the length. So we rotate it and then we unshear it. But let's think real quick, what is the determinant of a rotation matrix? Well, a rotation matrix, if you go way back when in your notes, a rotation matrix is the matrix that looked like this. Cosine theta, sine theta, negative sine theta, and cosine theta. So that was our rotation matrix from earlier. How did we come up with this? We came up with this by starting here, and then rotating it into a new vectors here, and then letting that be theta, and then doing all of our trig calculations. So this was our trig calculations. It would be worth kind of revisiting that at some point just to kind of remind yourself of how that works. But here's the question: what is the determinant of a rotation matrix? Well, the determinant of a rotation matrix is cosine times cosine, which is cosine squared theta, and then minus a negative sine times sine, so it's plus sine squared theta. And so cosine squared plus sine squared equals 1. So what's important is noticing that the rotation matrix has a determinant of 1. So that means that when you multiply by a rotation matrix, you don't change the determinant of your matrix. So if you have any matrix A and you multiply by a rotation matrix and you take the determinant of those, you're going to get the same determinant as the determinant A. Again, the determinant is not going to change by rotating. If we come back and we think of determinants in terms as somehow telling us the area of the transformation, then that makes sense, because if you rotate things around, it doesn't change the area. It just changes where it's located. So rotation matrices don't change the area. Now, what about a shear matrix, an unshear matrix, or a shear matrix? Well, we know a shear matrix looks like this. 1, K, 0, 1. Or the K could be down here. It just depends on whether you're shearing in the X or Y direction. Notice the shear matrix actually looks just like a row replacement matrix. And this determinant is real easy. And this determinant is equal to 1. And so that means this second action this action of shearing or unshearing also does not does not change the determinant of the matrix. So if you shear it, you get the same determinant as what you started. So basically, what we find is that this final rectangle, whatever this rectangle is, this final rectangle shape, after we've rotated and after we sheared it, is the same as the original parallelogram. And by the way, a rectangle is a really simple matrix. A rectangle matrix would look like this, A0, 0B, because we would go A in the x direction and B in the y direction, and then this determinant is A times B, which is length times width, and gives you exactly the result that we expected. So notice rectangles, the determinant gives us the area, and if you need any shape that's not a rectangle, you can transform it into a rectangle without changing the shape of the determinant. So this is cool. So this is a trick that works anytime you want to do geometry. And so if you want to find any sort of parallelogram shape, then all you have to do is you just have to take this as a vector 1, this as vector 2, and then you make your matrix with vector 1 here and vector 2 here, and you find the determinant of it. And that determinant is going to be the area or negative the area, depending on whether you're following the right-hand rule or the negative version of the right-hand rule. Okay, I think this is really cool. I hope you guys find it as interesting as I do, that the determinants somehow tell us the area of these things. Now what's cool, if you flip the page over, I'm going to give you a problem that's a three-dimensional problem, and this works even in higher dimensions. So we have this parallelepiped. Isn't that a cool word? Sorry, I'm saying the word cool a lot. I guess I'm hanging out too much with my 7-year-old son. Parallelepiped. And parallelepiped is really just a fancy word for a kind of not straight box. So if you think of a parallelogram as like we have a two-dimensional rectangle, and then a parallelogram is what happens when you take that two-dimensional rectangle and kind of bend it or lean it to one side. A parallelepiped is the same thing in 3 dimensions. So we have a normal rectangular box, and then if you make those sides, instead of making those sides right angles, you make them lean, so your box leans in different directions. You get a parallelepiped. So there's a vocab word for you. So how do you find the volume of a parallelepiped? Well, here's my attempt to draw that parallelepiped that I did. It's not a great attempt. You all know that I do my best, but it's never perfect. But here's my attempt to draw the parallelepiped. It's a box, but it's kind of got leaning to it, and this corner here is the original 3 vectors. Well, you might be able to guess what we're going to do. We're just going to write those 3 vectors down. And we're going to write those 3 vectors down as a matrix. 2, 0, 0, 0, 1, 1, and then -1, -2, 0. And then what am I going to do with it? Well, we know areas and volumes come from determinants, so I'm going to find the determinant of that thing. And this ends up being not too bad of a determinant, because if I just look at this first column, I can see that determinant showing up right away. And so the determinant is 2 times the determinant 1, 0, 1, -2. And then plus 0, I guess minus 0, plus 0. And it doesn't matter because you're multiplying by 0. This determinant now, we get 0 on this diagonal and -2 on this diagonal. So it looks like our answer is 2 times another 2. So it looks like 4 is the volume. So the volume of this parallelepiped, even as weird and as strange as it is, you get the same volume. If you wanted to do some sort of theoretical proof that this method works, you would do the exact same way. You would do a combination of rotations and stretches, and you'd find that all those rotations and stretches don't change the volume of the parallelepiped, but they result in a box whose volume must be the same as the determinant. This kind of brings us to really the way we think about what determinants are. And that is, if you think about a matrix makes a linear transformation. So if my matrix might take some sort of linear transformation that looks like this. So I've got some sort of rectangle. And maybe I have inside of that rectangle some sort of picture. Here, let's draw a picture of a flag. And now, what's my matrix going to do? Well, my matrix is going to transform that those two vectors, our E1 and E2 vectors, into new vectors. So maybe I get something like this for my new E1, for what happens when I multiply E1 by my matrix. And maybe I get something like this for my new E2 matrix. And then this rectangle becomes that rectangle right here. And now my flag now looks something like this right here. But the question is, what does the determinant of the matrix tell us? What the determinant of the matrix tells us is that if this has an area equal to A, let's not make, if this has an area, let's just stick it as area, then this one is going to be the determinant of A. This new area is going to be the determinant of A times the original area. So what the determinant tells us is how much stretching and pulling has changed the area of this shape to the area of this shape. And notice that that makes sense if you think about it in terms of those parallelograms, because what we've done is this box has a 1 by 1 area. So this has an area of 1. The determinant told us the area of this parallelogram, which is what that box got transformed into, and this parallelogram now has an area of A. So whatever your original area is, it got stretched and pulled in such a way that it is now whatever your original area was times the determinant of the A. So determinant tells you some sort of transformation of area factor. If you think of transforming a shape before and after, how big is your new shape is determinant. And this is why determinants show up all over the place. So whenever you're doing transformations in Calculus 3, you're trying to change coordinates before you do an integral or something like this, there's a determinant that shows up at the end. And the reason why there's a determinant is because you want to figure out what was your original area, how much did the area change after you made that transformation. Because if the area of all your squares, if the area of everything increased, then that means that your integral is going to be off by that factor, by however much that area changed. So you need to account for that determinant inside of that problem. And there's a lot of other places in mathematics that have this type of situation show up, where you have a determinant, and that determinant tells you how much the area has changed. Because we often worry about the transformation of area from one to another. Let's use this concept to solve what might be a bit of a tricky problem, unless you kind of know. This actually has an answer that maybe some people know, but I wouldn't expect most of you to know it. What is the shape? This shape is an ellipse. By the way, do you remember how to graph such an ellipse? Okay, perfect. Yeah, you're exactly right. This number tells us that the x diameter, I'm going to use diameter, I think, what do they call it? Man, I don't remember the word from geometry. But anyway, the length in the x direction is going to be 2, because that's a 4. And our y diameter is 5. So that means that our ellipse looks something like this, where we have, I shouldn't say, why did I say diameter? It's like a radius, and our y radius. Now, I know radius isn't quite the right word, because radius means you're talking about circles. What is like the major axis and the minor axis on the x direction and y direction? I think those are the phrases that we usually use. But let's just call them an x radius and a y radius. So notice our x radius has a length of 2, our y radius has a length of 5, and we get kind of this type of ellipse right here. So what's the area of this ellipse? It's a little tricky to do the area of an ellipse, but there's a really nice trick that's going to make this work out. And that is, how would you get from a well-known shape to this ellipse shape? Well, the well-known shape might be the shape of a circle. So what if I had the simplest possible circle, a circle of radius 1, a unit circle, and how would I go from a unit circle to an ellipse that looks just like this one? Well, the answer is this. If we have a circle on this side, unit circle. So on this side, I have my unit circle. What do I notice about that unit circle? I notice that this vector right here is the vector e1, and this vector right here is the vector e2 because it's a unit circle, it just has one in each direction. So now if I wanted to transform this into an ellipse that looks just like that one I have up there, then what would I need to do? This new vector would be pointing in the same direction, but it would now have a width of 2, and this would now be the vector 2, 0, and this one would now be the vector 0, 5. So that means that I know what my matrix is. My matrix is the matrix 2, 0, 0, 5, because all I did was I took this, I stretched it by 2 in the y direction and stretched it by 5, or 2 in the x direction and 5 in the y direction. And that has transformed my circle into my ellipse. Well, what that means is that I can use that principle that I had just a minute ago, and that is that my area of the ellipse equals the determinant of that transformation matrix times the area of my unit circle. And this is really great because these are things that are easy for me to calculate. So I have the determinant of 2, 0, 0, 5, and then times area of a circle. And this determinant is easy. It's just 10. So this is 10, and the area of a circle is pi r squared. R is 1, so it's just 10 pi. So what is the area of that ellipse? What is the area of that ellipse? Well, it's the area of this circle, which is pi, times a factor of 10, because 10 was the determinant of the matrix needed to transform that circle into that ellipse. So my answer is 10 pi. I don't know about you, but I find this a really interesting result. Okay, at this point, I'm going to let you go. There is a quiz. Last time I promised you one, but I lied. But that's because I kind of combined all 3 sections together in one quiz. So there will be a quiz attached to this one. Ignore the number on it. So I have some old numbers on it. I don't have my software to update the quiz numbers. I think this is going to be labeled quiz 13 or something, but we all know this isn't the 13th quiz in the semester, but we can deal with our quiz having the wrong number on the top, I hope. What you should look forward to is next time I'm going to introduce one of my favorite things in the semester, and that's Markov chains. And that's going to lead us to our last application problem, where you all get to analyze the games of Chutes and Ladders and the games of Monopoly. And I'm kind of disappointed we don't do this in class because this is really one of my favorite projects that we do. It's going to involve some big matrices, so it might be a little painful. I encourage you to reach out to your classmates and collaborate and work together. Find some times that you can meet together in study hall hours or even outside of study hall and work on these applications problems together. But that's going to be next week. This week, I want you to get really good at determinants. I want you to do your determinant homeworks, and I want you to do that quiz. So enjoy the rest of your week and your weekend, and I'll see you next week.